Thank you, Eula. So this talk is based on a research paper, but I'm going to try to give this talk as more of a kind of tutorial. Now, there are kind of two levels of results that I want to talk about. One is the results of the paper itself, which I think are kind of interesting. And the other is that this paper is kind of a model for how to do software, hardware co-design. So how do you design architectures and data structures in a kind of a post Moore's Law world, where the processors aren't getting any faster, and the only way you're going to get improvement is by creating specialized hardware to accelerate certain tasks. And so we're going to be asking questions about what kinds of hardware changes make sense, what kinds of things can we do with that hardware. And I think that, this meta level is more important for a school than these specific examples, but I think these specific examples are also of interest. So don't hesitate to, raise your hands and ask questions if there's something that you don't understand, some choice that requires a justification. So there's a basic fact of life which architects have been talking about for ages, is called the memory wall. Now this is an old, somewhat obsolescent diagram taken from a textbook, but it's still accurate. The idea is that the performance of processors is high, and it's improving for a while, and now it's sort of flat. Memory has not been able to keep up. So you can do much more computation on a modern processor than you can record in memory. And this is a fact of life that is not going to go away in the near future. And one of the big problems is how do we get around this particular problem in this particular case. So this shows up in a number of different ways. This turns into slow memory access. So the host processor, when it speaks to the memory can't keep up, so the host processor has to wait for the memory to respond, which wastes time. It's bad for performance and bad for energy. The normal way to approach this is you put it on chip cache. A small, high-speed memory very close to the processor, not to the memory. And you hope that you'll hit in the cache often enough to hide some of the latency and bandwidth issues. But over time, caches have become less effective as applications get bigger, because cache locality goes down as your data set gets larger and larger. So there's been a kind of a movement. This has been studied for decades on and off. Sometimes it's popular and sometimes it's not so popular, called near-memory computing. And here the idea is we take a very simple processor, in-order processor, no cache coherence, no address translation, none of those fancy things. And we put it physically next to the memory so that it has better bandwidth and latency with the memory. And the host processor, in some sense, uses this as a device. So it talks to the near memory unit and says, please invert this matrix for me. Please do this other computation for me. Let me know when it's done, and I'll go about doing something else. So the computation is offloaded. The near memory unit does this, and it sends the result back. So instead of doing the computation at the host processor and sending every little load and store to the memory, you give high-level instructions to the near memory compute unit, which will do the work on your behalf and report the response. Now this is great. The question is, why don't you have one of these on each of your laptops? Why hasn't this marvelous idea taken over the world? Well, there's a number of reasons which we'll get to. First, I want to talk about hardware enablers. So people first started talking about near memory computing in the 90s. Then none of the chip manufacturers paid any attention, so the area kind of died off, and now it's coming back. I'm going to give you a brief review of kind of recent hardware developments that make this approach more plausible again. One is 3D stacking. So one way to get a processor close to memory is by putting the processor physically on top of the memory. So you have, you have your logic here, and then data partitions all lined up, so that the physical distance between the memory and the logic is very small. You don't have to go off the chip or go a long distance. And when we're talking about speed of light considerations, this is a big deal. There's a couple of commercial proposals. You can buy things that are kind of like this. This is where the processor lives. There's another proposal which says that if you look at dual inline memory modules, they tend to have large buffer areas that are used to, basically for electrical reasons, to lower capacitance and things like that. But there's plenty of room for putting a small processor. And so it would not be that difficult in principle to squeeze a processor onto this, which has a direct access to the memory. So these are all proposals. Some of them are more real than others that make this near memory processing vision seem somewhat more realistic. So this would be our target. That you can buy something called a BB Cube 3D, which looks kind of like this. Again, the idea is that by placing things in 3 dimensions, you can move the processor close to the memory. Now, the processor has to be a very simple, low-power processor to fit. Here, there's no multi-threading, no multiple cores or anything like that. It's very basic, but it does do computation. So the architecture questions. NMP is one of these ideas that sounds good on paper. Does it really work? And more specifically, what can we actually do with it? Is it easy to implement and use? So, for example, can we use NMP applications to do better than the state of the art in some area? Maybe in some specialized area. There are lots of hidden overheads. So most of this talk I'm going to give talks about experimental results, where we find that things that should be easy aren't because of overheads that we kind of overlooked. So it's very much of a performance and systems paper, but this interacts with data structure design and other kinds of the more theoretical things that many of the people here are more used to. What hardware configurations make sense? There are many, many different ways you could take near memory processing and plug it into a system. Which ones are sensible and which ones are utopian? Again, how do we make this easy to reason about and use by mere mortal developers? So what we're going to look at are highly concurrent data structures as an example of an application area. So highly concurrent data structure is usually some kind of a hash map, or skip list, or B tree. And these are useful for things like in-memory online processing, OLTPs, online transaction processing. So these data structures lie at the heart of a lot of existing software. They have to perform well. They exist in order to perform well. You can provide them as managed package libraries. So, my graduate students can sit down and spend a year, debugging and writing these things, something you wouldn't expect normal programmers to do. But we can sort of plug them up into a library and say, here's the interface, you call this stuff, we'll take care of the rest. So we're not proposing a general kind of software development model. We're saying here are some data structures that you can include into a library where if your software needs happen to include skip list or B tree, then this will solve all your problems. So the challenge here is we want to figure out how to use NMPs in an effective way to build concurrent data structures. We want to preserve high concurrency, and we want it to be correct. You know, it's probably obvious to many of you that correctness is important, but my other 4 co-authors are all electrical engineers, and I had to throw temper tantrums from time to time to focus on correctness rather than performance. We need to keep a lot of locality is everything. If you have to transmit information over long wires, then you're going to lose this game. And we want to take sort of plausible near memory processing hardware and use it in a way that's plausible to the kind of people who work on this. So here's the baseline architecture. This is kind of standard computer architecture. At the top we have a bunch of host processors, cores. They have their private L1 caches. What's important is they have a large or medium-sized last level cache that they all share. So as long as your data lives in last level cache, then you're going to perform reasonably well. Notice that a lot of pointer chasing data structures, things like skip lists and B trees and so on, tend to work. When they get beyond a certain size, they tend to work poorly in these kinds of architectures because you're constantly dereferencing new pointers. So if you're going through an array, if you're linearly sequencing through an array, then caches work pretty well because when you fall off the end of your cache line, you pull in the next chunk of the array, you go through that. But if you're going through, you're dereferencing random pointers, then it's hard to get a lot of cache locality once your data structure gets to be too large. The main memory here is typically off-chip, and there's an interconnect between the last level cache interconnect and the main memory. Now, the first thing we're going to do is we're going to divide the main memory into kind of regular main memory and near memory processing cores. So the idea here is that this memory is not accessible to the NMP processor. The NMP memory is accessible only to the NMP core. This architecture makes sense because we don't want to worry about things like address translation. Virtual memory and all that stuff, that's hard to deal with. We don't want to deal with coherence. So if these things could share memory, we'd have to worry about what kind of coherence guarantee do we give. And the answer is we don't need to worry about coherence because the only way you can get here is by going through this core, and only this core can access this memory. So we avoid a lot of nightmarish questions by choosing a very simple kind of architecture like this. We're going to, within an NMP, we're going to use a technique called flat combining, which has been around for a while. This is a way of, in some sense, taking a lot of concurrent threads and mapping them onto a single thread. So the NMP core is going to share a small amount of memory with a host. You can think of this memory as kind of control registers. And each host processor can request an operation by writing into a piece of shared memory, saying, please add this key to the database. And these get to be lined up in something called the publication list. The NMP core, which is only one thread, will go through and execute these as it sees fit. It can do reordering, combining, and so on. We don't really do any of that stuff, but we could. And then when the NMP is finished with the data structure, it writes the result back into the control register. So the host can say, please do something for me, come back later and check and see whether it's done, and if so, what the result is. But the fact that we have one thread inside the NMP core which can handle each of these requests and return the response is critical for our kind of software interface. No, the data structure will be partitioned among the different NMPs. So each NMP has a piece of the data structure, and the host figures out which NMP partition it wants to talk to. So it says that all the keys A through L are in number 1, and L through Z are in number 2. And so it's the host process figures out what requests to make.
And you make
Yeah. And in fact, we're going to assume that these partitions are static, that we never need to move things from one to the other. You know, you could do that, but that would be a distraction in this context. So, you know, here's sort of an example. This is a skip list. I'll talk more about skip lists later on, where we've statically put everything from 1 to 8 here, you know, from 10 to 12 here, and 20 to 26 here. And each host processor, when it wants to do an operation, you know, add or read or remove, then it goes to the core that it wants. It writes its request into the memory, and these things happen. So the data structures here, the kinds of data structures we're going to look at are what we call hierarchical data structures, which map onto this kind of architecture fairly well. The idea is that the data structure is a hierarchy where the nodes at the top of the hierarchy are visited much more often than the nodes lower in the hierarchy. Specifically, we're going to look at skip lists and B trees. So this is basically useful for applications where you're doing key lookups. You know, again, we're thinking about online transaction processing applications. If you do this, there are lots of, well, there's a small number of algorithms for doing this in main memory, you know, lock-free skip lists and the like. And they suffer from poor cache locality because of this pointer chasing. That as soon as you do something, you need to dereference a pointer. That pointer is pointing into who knows where. You'll probably take a cache miss. And that's not very satisfactory. So as I said, we're going to be looking at skip lists and B plus trees, which are common hierarchical data structures. So I'm going to take a little bit of time to remind you what a skip list is. I'm sure many of you know this fairly well. But because the results depend a lot on the particular structure of skip lists, it's worthwhile to talk about this. So a skip list is a randomized data structure. It has a nice property that there's never any global rebalancing and has a logarithmic time search. And here is a kind of a schematic drawing. So the idea is that a skip list is represented as a hierarchy of paths with the property that each layer here is a sublist of the local layers. So this high-level one just goes from the first one to the last one. Then if we drop down one level, the second path is strictly larger than the first. So every path at one level is contained in the path at the next lower level. And as we go down, the number of elements can only increase. And when we get to the bottom, we get everything. So the bottom level path is everything in the database listed in sorted order. And one way to think of it is, as you go up, you skip approximately half of the nodes, which is where the name skip list comes from. And so this invariant, turns out, is not that easy to preserve in current implementations. So here's, for example, how a thread, a thread wants to say, is 8 in this list? And so it goes to the top and goes along the top level list, and it runs into 9 and says, well, 9 is larger than 8, so I overshot. I went too far. So in that case, I need to drop down one level. And so it's going to drop down and try it again. And then after its first hop, it says 7. Well, 7 is less than 8, so far so good. I'm closing in on it. Now notice that it skipped approximately half of the elements in the list in this step. So this is why this is a logarithmic search data structure, is because it's already skipped over half the elements. It continues at the same level and runs into the same problem that says, well, 9 is too big, that's no good. So it drops down and does the same thing again. Notice that all further searches start from 7. So it doesn't retreat. It goes, from 7, it drops down 1, that's still too high. And then it drops down another list, and this time it finds it. So at this point, it's skipped over, basically each time it goes, it skips over half of the remaining nodes. So this is a logarithmic search structure. The nodes at the bottom are much more rarely visited than the nodes at the top. In fact, the higher you are, the exponentially more traffic you get, and that's important for the experiments we'll do. So this is how you do a lookup. Inserts and removes are done in a similar kind of way. So each pointer, each layer jumps over basically 2 to the I nodes. Typically, you choose heights randomly. So summarizing here. So we have a sorted linked list structure with multiple layers. Each layer is a sublist of the list immediately above it. And it also, by its nature, it allows a fair amount of concurrency. So here, for example, we're reading 22, and at the same time, we're reading 10. And as you can see, the number of comparisons is fairly small. So what's the sort of obvious thing to do here? Well, to say, well, because this is a pointer chasing data structure, every time I search, I'm dereferencing pointers. This should be poorly suited for main memory, but it should work really well for near memory computing because we don't have caches and we don't have coherence. All the memory inside a near memory box is at the same distance. So let's take this and divide it statically into pieces and shove each piece into a near memory unit. And let's compare that to a state-of-the-art lock-free list. And when we did this, it turns out it didn't work very well. Now, we previously published a paper doing an analysis of exactly this sort of thing and argued why this should work really well. But when we built our simulation here, it didn't work. Here, skip list size is 6 times the last level cache size. We did some mixture of insert, remove, and lookup. So it performed fairly poorly just because of various overhead. All this little friction and sand in the gears that you get when you try to do this for real. It turns out that was enough to push this down below the curve, even though in theory it should work fairly well. Now, looking at this graph and the later graphs, higher is better. What we're measuring is throughput of operations, number of operations completed. Yeah.
How do you obtain these numbers? Where do you emulate the hardware?
Oh, this is Gem5 simulator. So this is completely a simulation. The grad student who was doing this for her thesis, configured the Gem5, plugged in all the numbers from these commercial sources.
Are you going to talk about that?
Yeah, it's all open source. I'll give you a link. I won't get into it too much because it's not very exciting, but we do have links to the source and so on. Yes.
What size the NMP was?
What size?
The NMP memory was.
LMP? The
NMP.
NMP. I don't remember exactly how big that was. That's something that the graduate student who did the actual work would know.
I guess seeing that skip list size was like 6 times sleep cache.
This is the last level cache size. So the skip list is 6 times the 1/6 of it fits in.
I guess I guess the cache the skip list did the NMP memory.
Yeah. So the skip list is better than you might think for cached memory because the small number of elements at the top are visited much more frequently. So you're more likely to get cache hits on those than on the lower level. So it's not as bad as it looks like it is, but it's still not ideal. So back to the drawing board. So this convinced us that we can't simply take our data structures and kind of shoehorn them into the near memory processing units. We needed to have some kind of a hybrid approach where we use both the main memory and the near memory processing. So the idea is, suppose that we have a cache that stores about half of all the data. So this is the last level cache. And everything that fits in here is good because we don't take cache misses when we once the cache is warmed up. And if we want to read something, what happens is most likely only the final access would go out to memory, or in this case, it would go out to the near memory processing. So if we can take just the hot part. Enough of the hot part of the data structure, put that in the last level cache, and put everything else in the near memory module. Then maybe we'll be able to make some progress. And in fact, when we did this, this was encouraging because now these two basically perform kind of the same. This is not a significant difference. But instead of being below the curve, it's still just a little bit above the curve. So that suggests that there's something to this idea of trying to put the hot part of your data structure into the shared memory cache and the cooler parts into the NMP.
So what's the benchmark here, Maurice?
Oh, the benchmark is you do random operations. 90% reads, 5% inserts, and 5% removes.
But you have placed the data in different memories. So does this mean that each memory has more or less the same amount of data?
Each of the near memory.
Right, and you have split it into parts, and now you have a specific memory storing the keys from a specific range.
If you go through the main memory part and you decide you need 27, you know which
part you're gonna.
You know where 27 should be, so you go there. So we're not trying to do anything dynamic among the different.
The insertions are all random in the entire key range. You expect that you have almost the same number of keys in each.
It's basically uniformly distributed. Yeah.
So you said before that there is a problem with pointer chasing which is not cache friendly. So now you're saying that okay, let us put the upper part into the cache. So how that's.
So if it fits in the cache, or even if most of it fits in the cache, then pointer chasing is not a problem because after a while you moved everything into your cache. Even more importantly, because all of the cold elements are locked up in the near memory processing unit, they don't pollute your cache. So one of the problems is I visit a very cold node, I only visit it once, that gets pulled into the cache and displaces something more valuable. So in this way we keep all the hot items together and the cold items separate. And this is the source of
But here, if you had more inserts and removes, I'm not sure, I'm just asking. I would expect that you somehow distribute the load, right? Because you can have all these NMPs performing concurrently, at the same time. So you may say, I'm going to insert 3 to the first NMP, 105 to the second, and all these happen at the same time. So I would expect to see a better performance here. So why? Is it because the 5% and 5% of inserts and removes?
No, because each of these, every time you.
Of the upper levels, what do you think is that?
Well, this is one of the issues we're going to track down in the course of the talk is what are the, but mostly it turns out to be lots of little annoying overheads. This is what happens to you when you go from, our paper analysis was glorious and wonderful, and the actual experimental thing was. So to test the sensitivity, we reran it with different size. This is the ratio of the cache size to the skip list size. And sure enough, as the data structure got bigger and bigger, then the cache became less and less adequate to contain things. So this is exactly what you would expect if our hypothesis was correct. That by making the data structure bigger and bigger, then we get more and more cache misses in main memory, and the performance should be poorer. So the conclusion is that even though the standard wisdom is that pointer chasing data structures don't live well with caches and memory hierarchies, this isn't quite true if you tune the parameters exactly right. So if the hot part of your data structure or most of the hot part of your data structure fits in regular memory, then you can do fairly well. But you do need to make sure that the cold parts don't contaminate the hot parts by being cached. Caching algorithms are greedy. They'll pull in anything that you touch, even if you're never going to touch it again. So this is what the skip list looks like. So in the host, we have the top part, the hot part in the main memory. Each NMP contains parts of the skip list. And we statically know, what the range of each item is, so that the host, when it decides to drop down into the NMP, it knows where to go. So, but it turns out that this is where correctness comes in. That if you do this in kind of a naive way, this isn't going to work. This isn't going to be correct. And that has to do with the nature of flat combining. So remember, the NMP core sits here and it looks for requests registered from threads, carries them out, writes back the response, and then picks up another request, and so on. So here's a scenario where we have the green thread wants to insert 5, and the purple thread wants to remove 4. And the green thread goes along and says, okay, this is, I've hit 4 in the main memory. Now I need to drop down and go into the NMP. And so insert 5 should begin at node 4, which is right over here. Now purple comes along, and it wants to remove 4, so it removes 4 from the main memory. Now it has to drop down and remove it from the lower level. So remember that removals go from top down. We need to maintain this invariant that each level list is a subset of the list below it. So if we remove something, we have to remove from the top down. If we add something, we have to add it from the bottom up. And so here says, okay, so remove 4, it realizes I have to go and work on 1. So both of these have been requested to have been registered with NMP core 1, saying, please carry out these operations on my behalf. And each thread is waiting for this to happen. And purple comes along and says, okay, I just removed 4 at both levels. That's good. The green thread comes along and says, oh, here's 4, I'm going to append 5. And I don't know if you can see the bottom of the slide there, but basically this is wrong. because the concurrency was messed up. So the insert appended the new item onto the end of an item that was being deleted, and that's because one is going bottom up, the other is going top down. So this is kind of a tricky. So how do we fix this? Well, we fix this in the most simplest, brutal way we can imagine. And so what we'll do is when we delete 4, instead of physically deleting 4, we're going to logically delete 4 and mark it as saying, this, I may look like a node to you, but I'm actually deleted. And if when the other thread comes along and says, I need to append to this, wait a second, this is marked as logically deleted, it simply panics and returns an error code to so the NMP comes back and says, sorry, I can't do this. And then the thread, when it comes back to look for an answer, it retries. So basically, this is still lock-free because if your operation fails, it's because someone else's operation made progress. But the simplest way to resolve these things is to say, we're going to detect these race conditions, and when they happen, we're just going to tell the host, sorry, we couldn't do this, try again later.
So here, marking happens at the next pointer of the last level, right?
Yeah. It happens at the 0 level. Yeah, at the bottom level. And don't forget, there's no concurrency inside the NMP core. There's only one thread. So if we put all these together, then it starts to look more serious. This is the benchmark, but in this particular one, for example, we get a 46% increase in throughput. Yeah.
Sorry, can we go back a couple of slides about insertions? Like, why do you need to specify which node do you need to start at? Can't the NMP core do the binary search itself to find the...
Well, you need to know which NMP core to go to. And it's also, the NMP core could start from its very beginning, but if you know that you're going to start at a particular node, then you may as well tell the NMP core, this is where I want to start and save the...
You don't have data rebalancing here, so each NMP core is always responsible for the same range of data.
Yeah.
So you can go straight to that core. The range doesn't... So you know from the beginning to which core you should go because you know the distribution.
When you don't necessarily know if the node is there, so you go down through the skip list, and when you when you know what node you want to start at, you also know which NMP core, but you don't want to tell the NMP core start at the very beginning because that might be too big. So I want to tell the NMP core, I want to start in the middle of the...
Okay. So did you try the approach that you can tell the core to start from the beginning, and then you don't have to do any magic at all because you have a single thread? I don't know whether the student tried that, but it doesn't seem very... It's... Yeah. Does regular skip list which doesn't use NMPs, doesn't it have the same problem?
Oh, the regular skip, it uses test and set in complicated way. The lock-free skip list will use the test and set to mark if something is been deleted in the same way. But it's different because there's actual multi-threading. You might have more than one thread operating on the same node. So it's a different. In the shared memory thing, there's no locks. All the threads are doing compare and swaps and tests and sets.
Yeah, but here we have a single NMP thread, so I guess that should be easy.
It's different. So it's not. It's single threaded inside the near memory core, but it's still kind of tricky because it's still simulating the operation. it could be interleaving things in its own way. So these aren't terribly difficult or subtle things, but I'm pointing out that you can't just kind of naively, saw up your data structure and drop it into the near memory processing and have it work. You have to watch out for concurrency bugs.
Yeah, also another question. You've said the problem with the regular skip is that it was written in the cache with lower levels. I checked, and there exists the assembly instructions that like move, but they don't move the values net into this cache. You don't want the value. Have you tried this?
I'm sorry, I didn't follow.
I checked the assembly instructions that try not to read for the main memory, but without the cache. Have you tried this? Have you tried implementing the skip list algorithm without the NMP in a way so the lower level accesses use the instructions which skip the cache, avoid values?
I'm not sure how that would work.
Well, this would work similarly to what you implemented, but instead of switching to NMP at lower levels, you would switch to instructions that don't button the cache.
No, we didn't try that. I think that would require some thought, I think, to make that work. You had a question?
Yeah, sorry if I missed it. We mark this nodes as logically deleted, but will we actually delete them on some later phase or not?
Will the basically we assume that eventually these things will happen. It's unlikely that you'll starve because that would require very specific conflicts, and all of the arguments are chosen randomly. So it's unlikely that you would have the same conflict over and over again.
Oh, okay.
Yeah, Maurice, it seems like you have to mark in all levels, right? Because otherwise, threads that are trying to update pointers at higher levels will take into consideration the removed node, although the marked node, because the node has been marked only at level 0, right? Whereas you need to transform this information up so that whenever you update pointers to remove this node, you update them correctly.
Yeah, I don't remember whether we mark all of the nodes or just the bottom nodes. Yeah.
It seems to be more complicated than what I was thinking. Okay.
I'm going the wrong way. Okay, so basically this improvement works across a lot of different. These are different workloads with different frequencies of the three operations. So it's fairly robust. So the next thing we did was let's look at a different data structure. And this time we're going to look at a B+ tree. So here too I'm going to pause a little bit to give you a review on what a B+ tree is, although I'm sure most of you are already quite familiar with this. So a B+ tree is an n-ary tree where internal nodes have navigation information. They tell you to go which direction to go in if you're looking for something, and the actual data lives at the leaves. The B plus tree rules are that each node has to be at least, in this case, half full, but it can't be more than, say, 3/4 full, except transiently during an operation. So that if your node gets too full, you split it into 2 nodes and readjust the tree. And if it gets too empty, you merge it with another node. So here, for example, we just overflowed this node. It's time to split. So we'll split it into 2 nodes. And then we have to go and update the navigation information in the parent. And now that node is too full. And then we split those nodes. So the basic idea is that it's possible that a split at one part of the tree will cascade up the tree. This makes concurrency kind of a challenge, because to make operations concurrent, what you really want to do is you want to localize their effects. But with these splits and merges, you can't really control. Some small change at some leaf may percolate all the way up to the root. It's infrequent, but it can happen. So we can do similar kinds of things merging up the tree. So basically, we have an n-rebalanced tree, data at the leaf, ordered by keys. In all our experiments, the node size is set to be the cache line size, because obviously that's what you want to do. And the nodes are always at least half full. So now we're going to try the same trick. So here, for example, we have a read. Each one marches through the tree. So for things like reads, there's a lot of possibility for concurrency. So we're going to do the same trick. We're going to put the higher level parts of the tree, which get the most traffic, in the host cache. And then we're going to put the lower level subtrees in the NMP. So this is the same kind of design philosophy that we used last time, and see how it works. What we'll see is that here too we have concurrency bugs if we're not careful. So for example, here I want to insert 57. So I go down to this node. I need to split it because now we're overfull. I update the parent. I need to split the parent. And so this is the cascading splits that are common to B trees. Now, why is this a problem? Well, here we have someone wants to insert 57. In order to avoid race conditions, we basically need to remember the path that we took. If we do need to do a split, then we have to go up and lock everything up to the root. Why is this necessary? Well, so here we have 2 concurrent operations, one that is reading 59 and one that's inserting 57. Both of them get queued at the NMP. The NMP goes to this node A, does what we saw before, splits it into 2 pieces. And so now read 59 comes along, and it knows or thinks it knows which block to go to, but that block was split immediately before it visited. And the key it's looking for is no longer available. So this is another example of a kind of a race condition that happens if you're not careful. The locking scheme that we saw before will help, but really what we want to do is we take those locks and we turn them into version locks. So a version lock is a lock whose state is an integer. And typically, if the integer is even, then the node is locked. If the integer is odd, then it's free. But each time you release the lock, you increment it. And so this is useful for things like ABA problems, where I read something, I look at something else, and I reread it. How do I know that I'm reading the same value? Well, if the version number is unchanged, then it's okay. So here, as we go through the tree, you just remember which version you're expecting. So here, everyone is expecting a parent to have a number 2. When we do the locking and splitting, we update the version number to a 3. And then when purple comes along, it says, oops, there's a version mismatch. And in our usual simplistic way, we simply report a panic to the thread, and the thread will retry at some later time. Okay, so you saw that we got some fairly promising results from the skip list. So we did exactly the same thing with the mechanism that I've described, which is pretty low overhead mechanism. And basically, we didn't get any performance at all. So this is another example of something that looks promising on paper. I could have stood up here and given you a paper design and explained what a great step forward in progress it was. But when we implement it, it turns out that it's it's no good. And why is this? Well, it's a combination of overhead. It's the fact that B trees tend to be very shallow. And so we didn't show the large fan out of the B tree makes for a very shallow tree. And so we didn't get all the benefits we were expecting to get. So question is, what can we do to save this situation? We wanted to make a B tree souffle, and we bring it out of the oven, and it's totally flat, and and the guests are arriving, and the paper submission deadline is arriving, and we need to turn this into something palatable. So there's another observation you can make, which has to do with the nature of control. Remember that we're treating the near memory as if it were a device. We're sending it a command, leaving it alone, coming back later, and asking for a response. But typically, the way we were doing things was we're treating like a procedure call. So we make the demand, and then we spend waiting for an answer. Which looks, the host comes along, it registers something, waits for the response, and then continues. And clearly that's not good because the host is idle while all of this is going on, and because the hosts are idle, the NMPs are underutilized. So everyone waiting on one side cascades into waiting on the other side. So a more sensible way to do this is to think of this more like a future than a procedure call. So we have the host comes along and it issues a request, and it remembers it issues the request. And so then it goes along and does something else, issues another request, and then eventually comes back and picks up the responses. And so by doing this kind of thing, then we get some decent numbers. So if we keep the threads busy doing these operations instead of waiting for the responses, then we get the numbers that look like this. Magical. And
What is the consistency you satisfy now? Is it still linearizability or?
yeah.
Now you have a thread having many.
Well, the thread itself is kind of multitasking, so it's like it's picking up jobs, and so it's linearizable. It has to do with the exact formulation of the model, but every operation is taking effect between its invocation and its response. It's just the threads are doing things in a confusing order. Yeah.
So could this increase be simply due to, have this solution having more processing units, more processing power? So kind of just how fair it is to compare a host-only solution to this solution to this last solution?
Oh, the host-only solution, all the host threads are busy all the time. So it seems like it should be fair, because in the host solution, all the host threads are doing their lock-free traversals. They're not idle. In the hybrid, the hosts are idle part of the time because they're waiting for responses from the near memory processing. So,
but basically, you have say 2 times as many cores in this hybrid solution, right? Where compared to just standard solution?
Well, the hybrid solution, there's arguably there's fewer cores because some of those cores are blocking. So I've got this big, multi-thread, this out of order core, but it's sitting there waiting for this, small memory device to come back and.
I'm asking about the last solution.
The last solution. What? All of these are. It's still the case that we're keeping both of the host and both the host threads and the NMP threads busier by cutting down on waiting, just by scheduling things a little bit more efficiently. So this is really more of a scheduling improvement than anything else.
Have you tried this non-blocking approach with skip lists?
That's the next slide.
And also, Maurice, have you tried to update the B3 top-down instead of the other way?
I'm not sure that that works. So you need to, if you insert something on the bottom, then it percolates up because you don't know at the top whether you're going to be splitting at the bottom. So you go down and at some point you say you insert something and say, oh, this is too full, I need to split. And then you say, okay, so I need to update the navigation. Oh wait, this is too full. So you don't know in advance whether you're going to.
Sequential model, you know. In the concurrent model, I'm not sure.
I don't think even in the sequential model you don't know because you don't know until you reach the root.
You don't know, but you do it. You always ensure as you go down that there is enough space in case there is any.
Yeah. There's always enough space to, but it's still the case that when you propagate the information up, you might need to split. Yeah, so we can do the same trick with the hybrid skip list and get even more performance. Yeah.
Sorry, what is the mechanism behind the non-blocking approach? Does the thread simply stores that it should come back later? Like, what does the host thread? How does it get notified of the?
Oh, there's a bit in the shared memory. So,
The host thread needs to pull the
yeah.
down instead of
Instead of spinning.
that it should come back in like 1 millisecond or something.
Yeah. So this is a systems paper, so there are no profound ideas. It's just a collection of tricks that.
It seems like you can get benefits from this non-blocking optimization only when the bottleneck is in upper levels of your data structure, not in NMP levels. Did you also have experiments where you have bottleneck in the NMP levels?
No, the whole point was to pick these hierarchical data structures where they're hot at the top. They're frequently accessed at the top and less frequently accessed at the bottom. Because otherwise, I think you would have serious problems. If your hotspot were inside the NMP, then I don't think that this would work. But that's another paper. Yes.
Can this non-blocking optimization be applied to the baseline of the version? I mean that, for example, theoretically check if the pointer is in cache, then descend, or if it's not in the cache, then ask to load it in the cache and try to do something else.
I'm having trouble hearing with, there's an air conditioner over here.
So I'm asking if it's possible theoretically to apply a similar optimization to the like baseline solution, which uses only main memory. Like check if the pointer resides in the cache. Yes.
It wouldn't really work in main memory because in main memory the threads are just busy operating directly. The main memory is shared. So it is not the case that nobody's waiting in main memory. It's a lock-free operation. All the threads are running as fast as they can. And so it's only because they block waiting for communication with the near memory processor that this kind of optimization makes sense. For the non-blocking operations, there's nothing to optimize because those threads are running as fast as they can.
As you mentioned, with these hierarchical data structures, there's a problem that basically lower levels are rarely accessed, but they're still getting cached, right? So I guess this near memory, I forgot what the acronym is.
Near memory computing.
Yes.
Near
memory computing, like you get the benefit of not having round trips to memory, of like saving some round trips, but you also get this kind of accidental benefit that you don't pull into cache.
Oh, yeah. It's not accidental.
I mean, like you could imagine, and as somebody mentioned, you have actual assembly instructions to read something without putting it.
Yeah.
So, kind of the question is, I guess you didn't compare, but your intuition is that how much of these benefits are coming from actual near-memory computing, or in how much just because we don't pull things into cache that we don't.
So it's not always that easy to disentangle all of these things. So the experiment that we did early on, where we had bigger and bigger data structures in the cache, and the performance went down, suggested that it was cache locality what was important. I think the not polluting the cache contributes to this. So if you pollute the cache, that's like having a bigger data structure. So I think you could probably do a paper analysis of that. So I think it's a non-trivial effect, but I don't think it's likely to be overwhelming.
But still, I guess you should check.
It would probably be easy to check, but the student is graduated, so she has a job, so she's not going to make any more.
Remember what's the branching factor of this? What's the branching factor of the B3?
Oh, I think the B3 was 4.
Oh, just 4.
Yeah. It was either 4 or 8. Actually, no, it was cache line, which means it was probably more like 8 than 4. So anyway, that you can look at the slides. We have the papers that we wrote on this subject at the top, other kinds of things to read about on the bottom. The simulator itself is publicly available if you want to experiment with it yourself. It's cycle accurate latencies for all the components, Gem 5 based simulator. This is something that only a graduate student doing a PhD will touch, because it would take 3 or 4 days to generate each of the points on those graphs, because it's all in simulation. This is the team. Everyone else is more of an engineer or an architect. I'm the only software person on the team. And let's see, that's it.